Okay, it's time to begin. Okay, so today we're going to talk about the Otter wrapper. That's the circuitry that goes around your CPU that interfaces your CPU to the input devices and the output devices. And I want to talk about hardware 6 and then also the final project. So the lecture portion won't be that long today. Okay, again, some of that depends on how many questions. But, you know, compared to most of the lectures, it will be relatively short. Okay, so the first thing, and a lot of what I'm going to say about hardware 6, I've already said. But once you know about the wrapper, you can also do the final project. Okay, and I just want to make sure you understand, you know, the differences between, you know, what's required for hardware 6 and then what's required for the final project. So first of all, hardware 6, that's due a week from tomorrow. Okay, so that's Friday of next week. That's March 3rd. And I think it was a week ago today. A meeting 11 or meeting 10, I think it was. Is this a meeting 12? I outlined how you would, in System Verilog or Verilog, model the control unit FSM. Okay. In fact, I gave you the state register code, right? I gave you the always FF block that goes in that FSM. It's just, you know, this statement with reset along with present state being next state. But the key thing is in hardware 6, that sample program that you'll run to test it, it doesn't have a load instruction. It doesn't have like a load word or a load half word or a load byte. Now it has an LUI, right? A load upper immediate, but like we talked about last time, the load upper immediate doesn't involve the memory module up where, you know, the DN and address to it. So, you know, it doesn't have the same data path as like a load word or a load byte. So the LUI doesn't need a write back state. It's like all the other instructions other than the load instructions. So because you don't have any load instructions in that sample program for hardware 6, your FSM for hardware 6 does not need the write back state. Right? This means your initial along with the fetch and execute. Okay. Also, during meeting 10 a week or so ago, I talked about the state decoder of the FSM. You know, we talked about how in the initial state, that's where you're setting the program counter to 0, right? You're resetting it so it starts at the first instruction at address 0. In the fetch state, you just need that memory read enable 1 to be active, right? Because that's what you know, that's what you need to have active in order to get the instruction at the output of the memory model. Okay, that's what we mean by fetch. Okay, that you're getting the instruction. Okay, now execute. The execute state, that's where the work is involved, right? Because in the execute state, you know, you're going to probably have some sort of like case statement where depending on what type of instruction you have, determines what the read-write enables have to be. Again, if you look at the Otter diagram, the output of the control unit FSM are reads and writes. Okay, and depending on the particular instruction you have, well, that's going to determine what, you know, read or, you know, what write has to be active. So again, before you do hardware 6, you need to have your diagrams that show the data path and the control signals for all your real instructions. On my previous sections today, you know, people would come up and ask, you know, questions along those lines. I would say, "Where's your diagram?" If they had their diagram, I was like, "Okay, let's look at it." If they didn't have their diagram, I was like, "Go get a diagram." You can't do this without a diagram.
So should we draw a diagram for like each and every instruction, or should we just try and draw one diagram?
You're going to need more than one diagram because how many have we done in class? We've done probably a dozen, right? Now, you don't necessarily have to have an individual diagram for every real instruction, because remember, you'll see there's gonna be a group of instructions where everything's the same except the ALU fund is different. So maybe you have one diagram for that, but you list, this is good for these instructions, but this is different, and that's your diagram. But yeah, you're gonna have more than one diagram. I don't know exactly how many. I mean, you don't need 37 or whatever the total number of real instructions are, but there'll be a number of diagrams that you'll need. Okay. There's another reason why you would want those diagrams that I'll get to later on. Okay. Also, for your control unit decoder, same thing. You need those diagrams because you got to see what the MUX selects have to equal for those 6 instructions that are in that sample program. Okay. And then you also have to, because once you have those control units made, right, your FSM control and your decoder control, you're now going to have all the pieces you need for your Otter CPU. Now, again, there's this piece of hardware labeled as CSR, which stands for Control Status Register. That's for interrupts, and again, we're not doing interrupts, so that's not going to be there. I put one of these diagrams that doesn't have that Control Status Register in the diagram. I put that on Canvas. It's right in the same place where this one is. It just says, without interrupts. Okay, because some people find it easier if that's not there. They see what they have. But you're going to have to connect all these lower level modules together, right? You've all done that, right? You did that for the program counter in this class, right? Because you have to connect the MUX and the register part of the program counter together. And also in CP133, I'm sure you did structural designs there. Okay. Also in that top module, you can put the 3 MUXes that you haven't designed yet. The only MUX you've done so far is the MUX for the program counter, but you need a MUX at each of the 2 inputs of the ALU, and you also need the MUX that's up by the write data input of the reg file. Now, the grading system and also the groups for hardware 6 are the same as what they've been for previous hardware assignments. Okay, so it's the same in-person groups and also the same submission that you make for grading.
I was just wondering, when we submit for hardware 6, do you want a simulation for like the FSM, the decoder, and the top, or just like the top module?
Yeah, for hardware 6, it's just the simulation for the sample program. So the sample program is the test cases, if you will, for this all together for those 6 instructions. Yeah, so you don't need an individual sim for the FSM. Yeah, that's another thing that's a little bit different. So I'm glad you brought that up. Okay, so once you've done all this, watch Dr. Hummel's video that's under meeting 11, and let me bring it back up and went to sleep here. So on Canvas, okay, this video here under meeting 11, you can see hardware 6, Dr. H. In this video, Dr. Hummel, starting at the 26.5-minute mark, okay, forward, he shows you the simulation for hardware 6 and shows you it right on the screen. So you'll know what it should look like. Also, remember you did the timing diagram activity last class, where you manually did the timing diagram for that sample program. Provided you did that correctly, it should look like that one also. And you can compare what you have to what Dr. Hummel simulation looks like, if you have the same. Okay. So that's really what hardware 6 is all about. I'm going to talk about some new stuff and then go over the final project hardware. But before I start to the new stuff, is there any more questions about hardware 6? Everybody knows what to do with it, an idea. You know, to get started on this, again, you need the diagrams. And then if you forgot, you know, what I had on the board when I outlined this for you, it's on Canvas. Right, I have it on Canvas. Okay. All right, so let's go ahead and talk about the auto wrapper. Now, before we get to the auto wrapper, there's this high level black box diagram of the Otter CPU. It's on your diagram sheet. It's up here in the upper left hand corner. So this high level black box diagram, it shows you what the main inputs and the main outputs are to your Otter CPU. And you can see you only have a few main inputs and, you know, 3 main outputs. I put the interrupt input in red because we're not going to have interrupt. So you can either leave it out, or if you put it there, just connect it to 0. Anyway, we got our reset. There's an IO bus in. We got our clock. And then on the output side, you just have an IO bus right. And IO bus out, that's where your data out is, and IO bus address. Okay, so I put this up here just to show you that when you do your clock module, these are your main inputs, these are your main outputs. All right, so this diagram here shows the auto wrapper circuitry around your CPU. Okay, here's your CPU here. The rest of what you see is what's involved with the auto wrapper. The auto wrapper was designed by Dr. Hummel, so you know it's provided. You don't design this; you just download it from Canvas. It's available on Canvas. Now you will have to make a modification to it. Okay, and I'll talk about that. But let's look at these, you know, different devices that we have in the auto wrapper, because you've seen most of them. I mean, what is this here? Right, that's it. Also, you have this module that divides the clock frequency by 2. If you were in my CP133 class, you saw that in CP133. I would imagine other CP133 professors probably talk about clock divide. Now, from CP133, and I also think I mentioned in this class, what's the clock frequency on the basis 3 board? 100 megahertz. 100 megahertz. So we're dividing that 100 megahertz down to 50 megahertz. Okay, so this is why you've been using a 20 nanosecond period, like in your, you know, SIM files and things like that, right? Because the 50 megahertz period is, you know, the reciprocal of that is 20 nanos. Now, the reason we're doing this, the reason we're dividing that clock frequency of the basis board down to 50 megahertz is just to have some wiggle room as far as efficiency goes. Okay, just in case you didn't design your CPU, you know, the most efficient way, well, by operating it at a lower frequency, you know, it most probably will still work okay. You know, provided it's not, you know, like extremely inefficient. Okay, so you know, this was to give some wiggle room, if you will, to give some margin. Okay, because it, you know, it's possible that a design would work at 50 megahertz, but not be efficient enough to work at 100 megahertz. So that's the only reason it's divided down like that. Okay, how about, let's see, how about, well, this over here, see, this is outputting to the 7-segment displays, and you may remember from CP133 that you need a decoder, right, to operate the 7-segment displays on the board. I don't think this is well, I know this is not the same decoder that we use in CP133. It's a different one. It's a Dr. Hummel design, but it's performing the same function as the one in CP133. Okay, how about here where we have these 2 devices here, E input, Q output, and enable, it's sequential. What kind of device is that? Flip-flop? Yeah, flip-flop. It's, you know, a register, right, for storing data. Okay, now this symbol you might have seen in CP 133. If you were in my 133 class, I don't think I ever talked about this, but what does it look like? It looks like a mux, but opposite, right? Because the mux here has a single output, multiple inputs, right? We're using the select line to choose one of the inputs to connect to the output. Well, this is just the opposite. It has one input, it's got multiple outputs, and there's a select input, but it's doing the opposite. It's connecting the single input to one of these multiple outputs based on what the select is. So this is called a demux. Again, it's basically opposite of a mux. Okay? So look at where the select line, see the select input of the demux and the select line of the mux, they go to this IO bus address of your CPU. So when we're reading from an input device, like when we're reading from your switches, right? When you're doing your assembly language program, and we did some sort of load instruction to get data from the switches. What address did we use for the switches? What is it? Not 40. It's a pretty long hex. Nobody remembers?
It's the 1100.
Yeah. Yes, the 11 and 60. Probably what you're thinking is the 114040. That's for the 7-segment display. And then what was the address for the LEDs? No, that's the 7-segment. The 40. 20 is the ending in 20 is the LED. So if this address is hex 11 and 6 zeros, well, that will select the switches and put that switch data here on the output of this mux that goes into the IO bus in of the CPU. So that's what brings in the switch data to your CPU. Now, this other input here for the mux, I just labeled as inputs, very general. Because the default, when Dr. Hummel designed this, the default is just to have this one input switch. But you can very easily add other inputs if you wanted to. Like you could add like a keyboard and give it an address, and, like a scanner or something, give it an address. Now in this class, again, because we didn't have time to talk about interrupts, we're going to be limited to switches. Okay, because to use a keyboard, you would have to have the interrupt available.
So does that mean buttons on the board also use interrupts?
Well, there's a different issue with buttons when it gets to what's called bouncing. So, I mean, you could, if you wanted to. In fact, there is a button that we have here for reset. I suppose you could use the buttons, but for when we get to the final project and I talk about it, you'll see there won't be a need for that. Okay, so over here on the output side, we got this demux like we talked about, and also the address, the IO bus address goes to the select of this demux. And you can see here, this output of the demux goes to this enable this register, and the output of this demux goes to this enable this register. So these registers are going to be holding data, and then the address through the enable is going to determine what device gets the address, or excuse me, what device gets the data. So if IO bus address here was 114020, right? The address for the LED. Well, whatever this IO bus write is, would now go to this enable of this register for the LED. And to write data to an output device, this IO bus WR has to be high, has to be a 1. So as long as this is a 1 and our IO bus address is the address for the LEDs, this register will be enabled, and then that data will go to the LEDs. And if this has an address for the 7-segment display, then this is a 1. Well, then this register will be enabled, and the data will go to the 7-segment displays.
So everything in the DMUX is basically just one bit? Every input and output?
Yeah, this is a single bit, right, and the enables are single bits, that's correct. Now, the address, this is like 32 bits. That's 32 bits, you know, the date is 32 bits. And coming in here is 32 bits. And I don't know if this switch is 32 or 16, there's only 16 switches on the basis board, but I don't know if they set some to 0 or not. I don't know, I don't think this is on the diagram, so I'm not sure, but we could look at the code later and find out. Okay. Now, the one modification that you're probably gonna have to make is that you probably will not have the same names for your inputs and outputs of your CPU that Dr. Hummel did. Okay, so a modification that you'll have to do, and I show this in one of my videos, is that you'll have to go into the wrapper module and you'll just have to edit these names to match what you have for your CPU. Okay, and in one of my videos, and I'll point out coming up, you know, I show you how to do that. I show you where in the code, you know, those connections are being made, and you know, you'll just have to go in there and, you know, make those edits. So it's, you know, it's very simple edits. Okay. In fact, let me show you where the other videos are. See, this video, like I said before, this is for hardware 6 and it's under meeting 11, but I have 2 other videos that are useful for both hardware 6 and the final project. They're under meeting 12. Okay, this is a video I made. And in this video, again, I show you where in the auto wrapper you have to, you know, make the modifications. And then this video here, Dr. Hummel's, this is a video where he shows you how to do troubleshooting of your final order, okay, the final project order. And I'll talk more about that video in just a second, but for right now, I just want you to know where these videos are, right? They're on Canvas. One is under meeting 11, the other one's on board. The other 2 are under meeting 12. Okay. So before I turn off the projector and lift the screen, because I got stuff on the other side of the screen, are there any questions up to this point? Are things making sense? Okay, all right, so let me shut this up, excuse me for a minute. All right, so now let's talk about the final project, because again, I want to make sure you see, you know, what the difference between hardware 6 and the final project is. So, you know, this is final project hardware. There's also a final project software that I'll talk about on Tuesday. Our last in-person meeting is Tuesday of next week, because I'll talk about the stack segment of real memory, along with how you do subroutines in assembly language on Tuesday. So, you know, at the end of Tuesday's class, you'll then be able to do the final project software. You know, I'll talk about that at that time. The other thing on Tuesday, I will have your midterms to return to you on Tuesday. I basically have finished them. I just got to record the scores, and also I scan exams before I give them back. So you'll definitely get them back Tuesday. Okay, so for the final project hardware, what you're going to have to do is you're going to have to modify your control unit FSM for hardware 6 so that now it includes a write back state, because your final project has to be able to process all the instructions, right? Not just 6. So if you have to process all the instructions, that includes load instructions, and load instructions need that extra state. Okay, so you're going to have to modify your FSM to have a write back state. You're also going to have to modify the execute of the state decoder of the FSM, because now you've got more instructions, right? So, you know, you're going to have like a bigger case statement, right? And you're going to have more opcodes. Okay. You're also going to have to modify the control unit decoder, because again, you're going to have more instructions. So you're going to have a bigger case statement, right, with more opcodes. Now, the good news is You won't have to modify the top module, right? Because if your top module is correct for hardware 6, it's gonna be correct for the final product. So that you don't have to modify. So once you've done this, then watch these videos. Okay, so watch the meeting 11 Dr. Hummel video. So the same video as this one, but when you get ready for the final project, watch what's before 26 and a half minutes. Okay, because before this, Dr. Hummel talks about how to look for patterns. You know, like look for patterns in your diagrams for your different instructions. Because by looking for patterns, you can reduce the amount of code that you have to use to model those control units. You know, I have a handout that's on every bench, and I'll talk more about that coming up. But that handout is to give you some examples of what's meant by looking for patterns. Okay. You're not graded on how efficient your auditor is. Okay. You know, I told my earlier sections today that I have 6 working auditors. You know, wasn't too impressed. My 8 to 11 section was very impressed. My 12 to 3 wasn't impressed. You're not impressed.
Are they in the same room? Or are they different?
Well, no, they see that's my point. Oh, thank you for that question, because that's my point. Those 6 auditors that are working, they're all different. They're all different. 3 of those auditors have interrupts. Okay. The other 3 don't have any interrupts. But the 3 that don't have interrupts, like what you're going to be doing, I did one of them. An ISA, a student who ISA'd for me in the fall, I have hers, and I have Dr. Hummel's. They all work. But if you were to look at those 3, mine's the most inefficient. I'll admit, mine's the most inefficient. It works, but it's not the most efficient. My ISA, you know, when I compared mine to hers, there were several times I looked and I said, boy, that's pretty clever. I didn't think of that, but that's pretty clever. And then Dr. Hummel's, when I looked at Dr. Hummel's and I compared it to mine, I started to cry. I mean, his is so beautiful. It's just so beautiful compared to mine. I mean, mine looks so like sick, you know, compared to, you know, he's just so efficient. I mean, it's amazing how little code he used to do it. It's just amazing. But the point I'm trying to make is all 3 of them work. And as far as grading goes, they're all the same grade. Okay. But if you can do things more efficiently, it can make your life a lot easier, right? Because there's less code to make mistakes. There's less code to look at when you're trying to troubleshoot it, and you will have to troubleshoot. Okay. So it's worth the time to look to see if you can identify patterns where you can take advantage of that and not have to write so much code. Okay. And that's what that handout hopefully will help you with. But, you know, as I state on that handout, by no means are all the patterns included in that handout. Okay. And that handout, it's optional. You don't have to answer those questions if you don't want to. You know, I put, as you can see here, I put the numbers without any answers, because once I'm done with the lecture part and you start working on your assignment, you can come up and write the answers on the board. And if they're right, I'll put a check mark next to it. If they're not right, I'll just put a comment. Okay.
By the way, when you're saying like efficiency, would you say like the higher frequency you can run at is probably a more efficient design?
Well, yeah, if you have an efficient design, then you can probably run it at 100 megahertz and it'll work fine. But if you have a so-so efficiency, then you know, it might work at 50 megahertz, but it won't work at 100 megahertz. You know, that's probably mine in all honesty, right? You know, Dr. Hummel's will probably work at 20 megahertz, or, you know, some lower frequency, but mine's probably borderline. Okay. But it works. See, that's probably the difference between like, you know, like a hardware person and a programmer, right? See, I'm a hardware person. If it works, I don't care if it looks pretty. If a programmer, right, they want it to look great. That's like, if you ever want to learn C and just know it really well and write like really clean perfect looking code for C, take Professor Bland. Professor Bland teaches a 1-unit C class, I guess, every other quarter, something like that. And again, same sort of thing. When I look at Professor Bland's code, I just want to cry because it's just so beautiful. You know, like when he does Arduino code, it's just so perfect. I mean, it's really something. All right, but getting back to this. Okay, so watch this video again, meeting 11, Dr. Hummel. Also, watch my video, okay, under meeting 12, because in my video, what I show you is how you check to see if your Otter CPU that you now have designed for all instructions, right, all real instructions, whether you can tell from the sim that it's running those instructions correctly. So there's this all test mem file, again, that we provide. In fact, either Dr. Hummel or Dr. Hyannis came up with this, or maybe it was a collaboration between both. But this all test mem file, it has like 4,000 lines of assembly code, like 4,000 instructions, something like that. It's a ridiculous number. It's a huge file, but it's checking every instruction to make sure every instruction works. So in this video, I show you what to look for in the simulation timing diagram to make sure it's going through that all tests mem file correctly. Okay, now also you would want to watch Dr. Hummel's meeting 12 video, because that's the one where he shows you how to troubleshoot. And again, you're gonna have to troubleshoot. Okay, you know, when I did mine, I probably had, I don't know, probably like 10 or 12 errors. You know, when Dr. Hummel did his, he had errors. Dr. Benson, she had errors. Everybody's got errors. There's just no way around it. You know, with me, most of them were silly kind of errors, you know, like I remember I connected a few things wrong. I also remember, you know, where the immediate generator is, and we take 25 bits of the machine code, right? Well, I took 24 instead of 25, like I was 1 bit off. You know, and that caused the problem. You know, so those were silly things. Now, I did have one major problem I remember because it drove me crazy, and that was there was a problem with my reg file. It wasn't reading right, or I don't think it was reading or writing correctly. It was really screwed up. And you know, I was able to troubleshoot it to know that the problem was in the reg file, but it looked fine to me. But what ended up fixing it, and I don't know why, because it should have worked the way I had it, but I had the 2 assigned statements for the async reads, right? Like, you know, we talked about that when you were doing that reg file. Well, when you have an assigned statement, my understanding is that it doesn't matter where you put it in the code. Now, you can't go in a block, of course, but you know, it doesn't matter the position of it because it continually happens. But for whatever reason, I had the always FF, and then I had the assigned statements underneath like that, and that's when it wasn't working. And all I did was move the assigned statements above the always FF, and it started to work. I don't know, you know, but it worked. So that just goes to show, the reason I bring it up, it just goes to show that, you know, a lot of troubleshooting is just being persistent, you know, not to give up, you know, because I knew the problem was in the reg file, you know, and I just said, hey, let me try this, and that's what solved it. So a lot of troubleshooting is just not to give up. But in his video, in Dr. Hummel's video, he goes through the process of how you go about troubleshooting. And, you know, he does 5 or 6 problems, like he intentionally puts in errors, and he shows you how to troubleshoot to find where those errors are. But more important than the particular error, because chances are you're not going to have the same error that he, you know, errors that he shows in the video. But what's important is to understand the process. Okay. You know, when you're doing the troubleshooting, you're gonna need this diagram. You're gonna have to have this diagram nearby. But a lot of times the error will first show up, say in the in the program counter. But then you'll find that the problem's not really there. It's something that's feeding into the program counter. Like it might be the branch address generator if it's a problem with the branch instruction or something. So a lot of times the error isn't where it first shows up. It's something before that. Okay, so it's learning how to trace signals and things like that. Also, you have to have an understanding of the instructions. That all test mem file that I just told you about that has like 4,000 lines of instruction of code. We have a text file on Canvas, so you can look at that text file. Okay, and you can follow it. Okay, so when you find an area where there's an error, you can look right there and say, oh, what does this instruction do? And then you can look at the timing diagram on Vivado to see if it's actually happening the way it should. Okay, so once your otter passes the sim with the alt test and you've done the troubleshooting and it's all good, then you have to test that same alt test mem file on the board. And this is when the wrapper is needed. So, when you're doing this here, you're just testing the CPU. You're not testing the CPU along with the otter or wrapper. But when you get to this part, now you've got to include the wrapper and you'll need a constraints file, right? You haven't needed a constraints file this quarter yet because you haven't downloaded anything to the basis board. But here you will download your design to the basis board and then check the alt test mem on the basis board. And in my meeting 12 video, I show you what it should look like on your basis board if it's operating correctly. And what you should see, and again, you can watch the video, but I'll quickly explain what it should look like. You should see the LEDs. The LEDs will light up in sequence from right to left. And then every time it passes a series of tests, because every time an LED lights, that means a test has been passed. And depending on the instruction that it's testing, there may be a series of 16 or more tests, or there may only be, maybe 5 tests. It just depends on the instruction. Some instructions take more tests than other instructions do. So once a series of tests are successful, the 7-segment display will increment by 1, and it increments in hex. And it will go from 0 to 24 hex. So what's 24 hex in base 10? 36. Right? And remember how we said there's like 30 some odd real instructions? So basically, every time it increments, that means you've had a successful real instruction.
Also, I think you need to move the camera.
Oh,
Some point
okay.
there.
Yeah, thanks. Thank you. I always forget to do that. Whoops. Got a picture of the ceiling. There we go. Thanks. Okay, so once you now know that on the basis board, it's passing the alt test, that means your CPU along with the auto wrapper is all working the way it should. Well, now we want you, or I want you, to program the otter to do something, right? I mean, this is what you've all been working towards. I mean, the whole reason you want to put that thing together is now you want to program it to do something. And what I'm requiring is that you just program it to do something that you previously wrote a program for, like one of the previous software assignments or one of the examples that I did in class. It can be any of those. And you'd have to put it into RARs and make a mem file out of it. Okay. Now, you will have to modify if you use switches, if you use one of the examples or one of the assignments that use switches, or if you use that, the one you just did, software 5, where remember you were calculating a difference and then outputting it to the 7-segment display, and you're repeatedly doing that. Well, for any of those cases, you would have to include a delay. You know, like if you're inputting data and then like you're going to input a series of data, like remember there was that one where you had to read in 3 consecutive switch data. Well, you would have to add some delay because you'd have to give time for the user to change the switches. And I did an example in class where I showed you how you could create a delay. You know, I think the delay we had was like a second or half a second. You know, you probably need something longer for, you know, most people. You know, what I did, because I would never ask somebody to do something I couldn't do, right? So what I did is I took the assignment where based on the value inputted from the switches, it would either multiply that value by 2 or divide by 4. You remember that one? It was a while ago. Well, I put in a delay of like 10 seconds to give me 10 seconds to change the switch data because I'm pretty slow, you know, right? So that's an example. So really you could take any of those assignments or examples, like I said, from the earlier in the quarter, but you'd probably have to add a delay. And you know, you would program your otter and then show that it's doing that program, show that it was successfully programmed. Okay. Now, unlike hardware 6, for this final project, you can have a group up to 4 people. All right. So, you know, you can still have 2 people if you want to stay with the same person and just do it with 2, that's fine. You can have 3 people. You can have 4 people. So like two-person groups could combine if they wanted to. No 5-people group or anything more than 5. 4 is the max. If somebody wanted to do it by themselves, that's okay too, although I would not recommend it. The reason why I'm allowing up to 4 people is because this is a lot of work, especially when you get to the troubleshooting. The troubleshooting is likely to take some time. It's not easy. Okay, I'm pretty good at troubleshooting now. I'm much better at troubleshooting hardware than software. But still, I have pretty good troubleshooting skills. It took me an afternoon to get mine to work. I mean, I started like around lunchtime and it was around dinner time when I finally got it to work. You know, it's just not easy, you know. Also, you're being evaluated on getting it to work. So, you know, our last in-person meeting, like I said, is Tuesday. The class a week from today is an open lab. And then the last 2 weeks, there's no new material because that time is devoted for you to work on not only this hardware project, but also there's a software project, okay? And I'll be available on Zoom to help, but I'm not gonna find the problem for you. What I will provide is guidance. So if you're stuck, you know, I'll say things like, well, did you try this? Did you check this? Where does the problem first arise? Well, did you check that what's inputting to that? You know, those types of things. I'm not going to look at your code and say, oh, there's the mistake. You got a 2 instead of a 3 or something. Okay. So you're being evaluated on the troubleshooting. The other thing is the grading criteria is different for the final project hardware. And I put that grading criteria on Canvas. I'll talk about it in more detail on Tuesday because we'll be done with the software on Tuesday, I'll also be able to talk about the grading criteria for the software project. So I'll do that all at once. But if you want to look at what the grading criteria is for the hardware, you know, before Tuesday, it's on Canvas. Okay, so is there anything else? Oh, one other thing I wanted to say, this should make you happy. The SIM file for both hardware 6 and the final project, the simplest SIM file you'll ever have. All you need in the SIM file for hardware 6 and also the final project is you'll need the code to generate the clock. And then you just got to set reset to 0 so you don't reset it. Okay, and it's just going to run the mem file. I mean, the mem files are your test pieces in both of them. You have your sample program here, and then your all test here along with, you know, what you decide to program is like when everything's working. Okay? So do you have any questions before you get started? Because the rest of today's class is to work on whatever you want to work on. Again, that handout is optional, but I highly recommend that you go through it, and anyone can come up and write an answer when they have it, and I'll mark whether it matches mine or not. Okay? All right. Hi, Blake. Did you leave something? Sorry.